All right, Raiders, let's keep working on our forces of Newton's laws of motion problems packet here. So take a look at number 9. What is the average net force exerted by a shot putter on a 7-kilogram shot if she pushes the shot through a distance of 2.7 meters and releases it with a speed of 12 meters per second? So again, the parenthetical average there is just kind of a acknowledgement of the fact that every instant that she's pushing the shot, it's not literally going to be the exact same force she's exerting, but collectively over the time of her throwing the shot, what's going to be the net force. So nowhere in here do they use the word acceleration, but if you just think about the logic of what's happening, the shot putter that's kind of standing stationary in the shot put circle, they get ready to throw the shot, and then they release it with a speed of 12 meters per second. It has to accelerate to go from not moving to going 12 meters per second. So that's how we know we're going to use F net equals ma. And once again, just like we saw in 5 and 6 and 8, there's a lot of references to quantities of the motion. So sure enough, if we look at what's going to happen here, we're going to have to do some kinematic equation analysis here. Because what is the net force? So this is what we're looking for. We just need to know the mass and the acceleration. Well, we know the shot's mass, 7 kilograms, but we need to know its acceleration. So here's where we'll cross over into some kinematic equation work. So our given information, the shot putter, when they pick up the shot and they're getting ready to throw, they're not moving, so the initial velocity of the shot is 0. And when it leaves her hand, so that's the final velocity, is 12 meters per second. And she generates this velocity change over a distance of 2.7 meters. So we can find acceleration. So this combination of variables sets up, again, for Vf squared equals Vi squared plus 2AD. 12 squared equals 0 squared plus 2 times the unknown acceleration rate times the displacement of 2.7 meters. So 144 equals 5.4a. Divide both sides by 5.4. So the acceleration she puts the shot through is about 26.7 meters per second squared. So this will be the acceleration that we're going to substitute here for A in Newton's second law, F net equals ma. So a 7-kilogram shot put accelerated at about 26.7 meters per second squared. So she's exerting a force of about 186.7 newtons. Okay, number 10. How much tension must the rope withstand if it's used to accelerate a 1,000 kilogram car upward at 1.2 meters per second squared? So this must be like a junkyard or something like that. So let's see, here's our car. And once again, just like the last time I drew a car, don't get jealous about the fact that I'm really good at it. You keep working on it, you'll get good at it too. So let's see, it's pulled upward. So that'll be force of tension. Again, if you prefer more generically, F sub A for applied force, that's fine. And it's a 1,000 kilogram car. So that tension from the rope has to work against the force of gravity or the weight of this car. So it's mass times gravity. So mass of 1,000 kilograms times 9.8. So it weighs 9,800 newtons. Now, you can see the word accelerate here. So the either or test, either the object's in equilibrium or it's not. It's not. So it's not F net equals 0. It's F net equals ma. And remember, net force is not one specific force. Net force just means the combined effect of all the forces acting in whatever direction you're analyzing. So we're analyzing the upward vertical y direction here. And if you look at our free body diagram, both of these forces are in the y direction, so we have to include them both. So the net force is the combined effect of the tension of the rope pulling up, working against the weight of the car trying to pull it down. Collectively, they're going to make this 1,000 kilogram mass accelerate at 1.2 meters per second squared. So if we stick with the convention of up is positive, down is negative, Now that we're about to put specific numerical values in for forces, now we'll take into account forces of vector quantity, direction matters. Initially I just listed the forces being combined. Well, now the force of tension up is positive. The force of weight against that is negative, so it's plus negative 9,800 or just minus 9,800. So add the weight to both sides, plus 9,800 to both sides. So the force of tension here, did I put my, put the comma in the wrong spot there. So the force of tension is 11,000 newtons. And just taking a step back to see if that answer makes sense, the force of tension up needs to be more than the weight. That's why it accelerates up. So very generically, that checks out. All right, moving on. A 12 kilogram bucket is lowered by a rope in which there's 70 newtons of tension. What is the acceleration of the bucket? Is it up or down? Well, as far as the acceleration, they said it's lowered, so it has to be in that direction. And because they just said, what is the acceleration? Then you know that either or test, either the object's in equilibrium or it's not. So it'll be Newton's second law, F net equals ma. So let's draw our bucket here. 12 kilogram bucket. And we've got gravity trying to pull it down. Whether the bucket's stationary on the way up, on the way down, doesn't matter. Gravity always tries to pull everything straight down. So 12 times 9.8. It weighs 117.6 newtons. And then what's keeping it from plummeting to the ground is the rope pulling up with 70 newtons of tension. So you can see there's a disparity here between these forces. So the either or test, either the object's in equilibrium or it's not. So either by looking at the free body diagram and just seeing the forces are not equal and opposite, or the use of the word acceleration to describe the bucket's motion, multiple ways you can tell, oh, it's going to be F net equals ma. So the force of tension and the force of weight are competing against one another to make this 12 kilogram mass accelerate. So the force of tension up is 70 newtons. So if we stick with the convention of up is positive, down is negative, 70 plus negative 117.6, or just 70 minus that. Those two forces will be responsible for the 12 kilogram bucket accelerating. So the net force is downward, 47.6 newtons. And that's going to be responsible for the 12 kilogram bucket accelerating downward. Divide both sides by 12. So the bucket's accelerating at about negative 3.97 meters per second squared. And taking a step back, very generically, this should make sense, because if there was no rope holding the bucket back at all, it would accelerate downward at free fall, 9.8 meters per second squared downward, or negative 9.8. But the tension in the rope, even though it's less than the weight, it still holds it back at least a little bit. So this acceleration has to be less than negative 9.8. If you had gotten negative 9.8 or more than negative 9.8, you would have done something wrong. Okay, take a look at 12 here. An elevator of mass 4,800 kilograms is to be designed so that the maximum acceleration is 0.06 g. What are the maximum and minimum forces the motor exerts on the cable? So a couple things before we dive in. First, let's just address this right here. Based on the wording of some of our other problems, it would be understandable to look at this and say, oh, it's a reference to 0.06 grams, as in a mass. But in this context here, notice what they're saying. The maximum acceleration is, so that wouldn't really make sense to then describe the mass of something, because part of the sentence before says the maximum acceleration is 0.06 g. So in this context, the g references acceleration of gravity. So this is just another way to say 6% of gravity or 6% of free fall. So all you really need to do, if you want to find the percent of something, you multiply the percent by it. So 0.06 times 9.8 . So the acceleration the elevator is going to experience is 0.588 meters per second squared, because that is 6% of gravity. And that's just sort of a logistical design consideration from the engineers who designed the elevator. You don't want to have people thrown up on your elevator because it's like an amusement park ride. So they just keep it at a very small acceleration relative to free fall. Okay, so now the question says, what are the maximum and minimum forces the motor exerts in the cable? So really what's going on there, if you think logically without bogging this down with numbers, if you're going to lift something up against gravity, that's harder than just lowering something down. If you think about like if you take a backpack off your shoulder and you lower it to the ground, it's easier to do that than it is to lift it up against gravity. So that's really what's going on here. In one case, the maximum force exerted by the motor is when the elevator is on the way up, and the minimum force is when it's on the way down. So we'll look on the way up, which will be the max force. And then separately would be the way down, which would be the minimum force. So we'll draw a free body diagram showing all the forces that are acting here. So here's our 12 kilogram, let's looking at the problem up above, 4,800 kilogram elevator. So the weight of it, 4,800 times 9.8. It weighs 47,040 newtons. And then the tension up from the motor. So I just called it force of tension because it's a force exerted through a cable. And anytime a force is exerted through a rope or a chain or a cable, we generically call it force of tension. But if you want to more directly call it the force of the motor, that's fine, doesn't really matter. Now, if this elevator were either stationary or moving with constant velocity, it'd be in equilibrium. The force of tension or the force of motor would be equal and opposite to the weight. But if it's going to accelerate up at 6% of gravity, then we know the forces are unbalanced. So it's going to be F net equals ma, Newton's second law. So the net force, the combined effect of all the forces in the line of motion we're talking about. So in this case, it's both of them. The force of tension plus the force of weight. They're going to compete against one another to make this 4,800 kilogram elevator accelerate at 6% of gravity, or 0.588 meters per second squared. So we stick with the convention of up is positive, down is negative. Tension up, which we don't know, that's what we're looking for, is up, that's positive, that's working against, so plus negative the weight, or just minus the weight, 47,040 equals the mass times acceleration. So it's going to equal 2,822.4 newtons. So the 2,822.4 newtons, that really is, if you just take a step back, that's the amount of unbalanced force acting. So we'll add the weight to both sides, plus 47,040 to both sides. So the force of tension the maximum force of tension in the cable is 49,862.4 newtons. It has to be more than the weight in order to accelerate it up. So now on the way down, same free body diagrams, the same forces, and it's the same situation since you have acceleration, still F net equals ma. But notice what will happen here. So the force of tension up plus the force of weight, they're going to make this 4,800 kilogram elevator accelerate. Now it's going to be going downward, so it's going to be negative 0.588 meters per second squared, because acceleration is also a vector, so we have to take into account direction. So the force of tension up minus or plus negative the weight of 47,040 newtons. The weight's negative because it's on the way down, equals negative 2,822.4. Add the weight to both sides of 47,040. So the minimum force of tension, because it's easier for the elevator to be lowered down, since you don't have to completely cancel out gravity. So this minimum force is 44,217.6 newtons. And again, just reflecting on the answer, the tension in the cable up from the motor is less than the weight. That's why it accelerates down at 6% of gravity. Okay, 13, for all you aspiring art heist participants out there, an 80-kilogram thief wants to escape from a third-story jail window. Unfortunately, a makeshift rope made of sheets tied together can only support a 60-kilogram person. How might the thief use the rope to safely escape? Give a quantitative answer. So as soon as you see that, you have to have a calculation-based answer. You can't just kind of come up with some, clever action movie solution to this. So we'll draw a free body diagram of our thief. So their weight, or the force of gravity pulling down on them, mass times gravity. They have a mass of 80 kilograms times 9.8, the gravity. So they weigh 784 newtons. But the problem is the force of tension from their makeshift rope can only handle the mass of a 60-kilogram person. So this one looks a little tricky, but really the way they just say it can support a 60-kilogram person. In other words, what they're basically saying is figure out the equivalent weight of this that this can handle, and that would be the force of tension. So 60 times 9.8. So it equivalently can handle 588 newtons of tension. And again, force is a vector quantity, direction matters, but like we talked about in earlier videos and in class, if we stick with the convention, up is positive, down is negative, they are going to have different signs, but when you just identify a force in isolation, we just say the tension in the sheets, the makeshift rope, would be 588 newtons, and the weight of the person, the thief, is 784 newtons. We wouldn't have to say negative 784. But once we start doing some calculation-based analysis, we will take into account directional positive and negative signs. So what's going to end up happening here, you do have to be a little creative to recognize what's going on here. But again, the either or test applies. Either the object that you're studying, the thief, is in equilibrium, or they're not. Well, if you think about this, if they very cautiously climb down the rope, just kind of hand over hand, kind of slowly, methodically moving at a constant velocity, then the tension up would be equal and opposite to the weight, but we already know that can't happen. The rope made of the sheets cannot handle 784 newtons of weight. And if they ignored the rope and they just jump down, they're going to end up breaking both legs because they're going to accelerate so fast, free fall, 9.8 meters per second squared downward, that by the time they hit the ground, they're going real fast, they're going to break their legs. So this makeshift rope of sheets here, they're going to just be a little creative. They're going to hold on to the sheets and slide down, but they're only going to partially hold on. They're only going to use it to cancel out some of their weight. So it's going to just slow down their acceleration rate. So they're still going to get faster and faster and faster as they go. But by not subjecting the sheets to their full weight, they're going to accelerate something a lot less than free fall. So we're still going to use Newton's second law here. F net equals ma. The force of tension from the ropes plus the force of weight trying to pull them down is going to make this 80-kilogram thief accelerate. So the force of tension up is 588 newtons. The force of weight down, 784, equals 80A. So collectively, there's 196 newtons downward, making their 80-kilogram mass accelerate. So divide both sides by 80. So now they're going to accelerate downward at a much more manageable 2.45 meters per second squared downward. Now, obviously, that doesn't guarantee they're going to be safe. They're going to get faster and faster and faster as they hit the ground, but they won't hit the ground as fast as if they just jumped. And I don't know what to tell you. If you're picking a life of crime, it's risky business, so that's just the way it is. All right, 14. The cable supporting a 2,000-kilogram elevator has a maximum strength of 20,500 newtons. What maximum upward acceleration can it give the elevator without braking? So if we draw our free body diagram, here's our 2,000-kilogram elevator, and we have the force of tension, or again, if you prefer more directly, the force of the cable. Maximum strength of 20,500 newtons. And that's working against the force of gravity, or the weight of this elevator, mass times gravity. So 2,000 times 9.8. Excuse me. So it weighs 19,600 newtons. So if you look, the cable pulling up exerts a greater force than the weight, so that imbalance, it's going to accelerate up. So the either or test, it's not in equilibrium, it's going to accelerate. F net equals ma. So the force of tension up is working against the weight to make this 2,000 kilogram elevator accelerate. So the force of tension minus the weight, 19,600, equals 2,000 A. And we know the force of tension, 20,500 newtons. So this imbalance of forces, 900 newtons pulling up, is going to make this 2,000 kilogram mass accelerate. So divide both sides by 2,000. So we get that the acceleration of the elevator is 0.45 meters per second squared. Again, if you think about the other elevator problem we did, it's a pretty slow acceleration rate, which it should be, because once again, they don't want to make the people on the elevator sick. So they don't want to have it be like an amusement park ride. Okay, moving on. So let's take a look at 15. And this will be the last one we take a look at for this video here. So this one's a little more intricate here. An exceptional vertical jump would raise a person off the ground 0.75 meters. To do this, what upward force must a 65 kilogram person exert against the ground? Assume the person crouches a distance of 20 centimeters as they prepare to jump. Okay, so with this problem, we've talked about this in class before. One of the problem-solving strategies is try to go right to the answer that you need right at the end, kind of like solving a maze backwards when you know where you need to end up. And what you're going to see is we don't have nearly enough information to just solve this problem in a straightforward manner, but once we see what information we're missing, then that kind of tells us how we can go backwards from there. And another thing to keep in mind, if you were to just watch this person jump, visually it would be one smooth, uninterrupted thing to see. You'd see the person crouch down, you'd see them jump up, push against the ground, their legs are in contact with the ground as they extend up, then you would see them in the air. But in terms of analyzing this mathematically, we can analyze this as two distinct blocks of time. Because when the person is on the ground and their feet are in contact with the ground, they're going to experience very different things than when they're in the air and in free fall. So if you look at what the question's asking, what upward force must the person exert against the ground? So what we care about is their force on the ground. So ultimately, trying to jump right to the answer, we want to do F net equals ma. And again, the either or test, it's not in equilibrium. This person's going to accelerate up. They have to get up to some velocity in order to get 0.75 meters off the ground. So while they never use the word accelerate in here, we know this is going to be an unbalanced forces situation. It's not going to be equilibrium. So F net equals ma. So we have their force up working against the force of their weight, responsible for this 65 kilogram mass accelerating up. So if we were to draw a free body diagram of this person, we got the force up, and that'll include really the force of their legs plus the normal force of the ground pushing back against their weight, but generically I'm just going to refer to it as the force up. And then we got the force of the weight, and if there's 65 kilogram mass times gravity, 65 times 9.8, they weigh 637 newtons. So very generically, the force up has to be more than 637 newtons in order for them to actually accelerate upward to leave the ground with enough velocity to get 0.75 meters up in the air. Excuse me. All right, so we know the force of weight here. So we want to know what upward force. So this is what we're looking for. Well, seems like we're off to a good start here because we know the force of weight, and that's, if we go the convention of up is positive, down is negative. So it's the force up minus their weight will be responsible for their 65 kilogram mass accelerating. But notice we can't solve this. One equation, two unknowns. We don't know the force up, which is what we're looking for, and we don't know their acceleration on the ground. So we should be specific here. Since this problem can be broken up into segments, what's happening when they're on the ground versus when they're in the air, we've got to make sure we're keeping it straight in our own heads. So we're analyzing on the ground here. So really what we need to know is, what is their acceleration rate as they transition from being crouched down 20 centimeters to the last instant their feet are in contact with the ground. We need that acceleration rate. So if we kind of move a step over from there, also while they're on the ground, let's try to analyze this with kinematic equations. So we know when they're on the ground, given information, their initial velocity is 0 meters per second. They're crouched down, they're ready to go. And we know they crouch down 20 centimeters. Well, there's 100 centimeters in a meter, so 20 divided by 100. The distance over which they're going to get themselves up to speed is 0.20 meters. And we want to know their acceleration rate. But notice we don't have enough information here. We're kind of missing something. We're missing a puzzle piece. We need to know their final velocity. We need to know their final velocity on the ground. So here's where you got to be a little creative. Yes, if you just watch this person visually, you'd see one smooth, uninterrupted motion of them crouched down on the ground. They push against the ground. They uncoil their body from the 20 centimeters that are crouched down. And then you see the last millisecond their feet are in contact with the ground, and then they're up in the air. Well, if we think about that transition from the ground to the air, the final velocity on the ground, the last millisecond their feet are in contact with the ground, also becomes their initial velocity in the air if you think about it on the way up. So we can now analyze when they're in the air. And let's see what we got here. So if they get to a height of 0.75 meters, we know symmetry of motion, what happens on the way up happens on the way down. So let's just think about on the way down, because whatever happens on the way up happens on the way down. So we could say, okay, when they're in the air, on the way down, their initial velocity was 0. We know their acceleration rate, they're in free fall, negative 9.8 meters per second squared. And they went a distance of 0.75 meters, so displacement is negative 0.75 meters, because they went 0.75 meters down. We can find their final velocity. So their final velocity on the way down in the air is also another way to say that's how fast they were going as they had left the ground. So we can do VF squared equals VI squared plus 2AD. So VF squared equals 0 squared plus 2 times negative 9.8 times negative 0.75 meters. So VF squared equals 14.7. Take the square root of both sides. So they hit the ground going about 3.83 meters per second. Now, obviously, when you take the square root of a number on a calculator, it's going to give you a positive number, but I just parenthetically put a negative sign because on the way down, they're moving downward, velocity is a vector quantity. So the correct answer would be on the way down, they hit the ground going negative 3.83 meters per second. But with symmetry of motion, if they hit the ground, if they come back to the ground at 3.83 meters per second, that means they left going 3.83 meters per second. So that's also the initial velocity of their jump. And the initial velocity of the jump equals their final velocity on the ground. So we can substitute this value right there. So now we can do VF squared equals VI squared plus 2AD. But this is why it's important to keep the segments different. Yes, it's the same equation, but we're analyzing a different point in time. So if they're going to, the last millisecond they're in contact with the ground, which is also how fast they're going when they jump, had to be 3.83, about 3.83 meters per second. So 3.83 is approximately equal to 0 squared plus 2 times their acceleration rate, which had to happen over a distance of 20 centimeters or 0.20 meters. So 14.7 is approximately equal to 0.4a, divide both sides by 0.4. So their acceleration rate while they're on the ground is 36.75 meters per second. So it's a pretty fast acceleration rate, but that's why it's hard to jump high. You have to have enough power to generate this kind of acceleration. So that's their acceleration while they're on the ground. So now it becomes pretty straightforward from here. Their upward force, which again is really the combination of the force of their legs jumping up plus the normal force of the ground pushing back, minus the weight, is going to be responsible for this 65 kilogram person accelerating at 36.75 meters per second squared. So that equals 2,000, mass times acceleration equals 2,388.75. Add the weight to both sides of 637. So the upward force that they have to exert ends up being about 3,025.75 newtons. Okay, we'll stop there for now.